Good morning. Some of you have been asking, are we going to learn to go the other way? We've been deriving. Are we going to learn to essentially underive? And that's exactly what we're going to learn to do in Chapter 4, Section 1. It's on antiderivatives and the integral. A couple of comments on notation first. This little squiggly line that's out in front right here, that's the integral symbol. It's sort of like a stretched out S. The function that you are integrating, we're going to refer to as the integrand, and there will always be a dx after the integrand, and that's the variable of integration. It's sort of like the integration version of dy dx. For now, we're pretty much going to ignore it. It'll come into play a little bit later on in the year, but for now, just know that dx is always going to be a part of the integral. So this is obviously a pretty important slide. It's on the fundamental theory of calculus, right? You don't get much more important than the fundamental theory of calculus for indefinite integrals. It basically states that the integral of some function f of x is equal to what we're going to call the big F of x plus c. And what's big F of x? Big F of x is the antiderivative of little f of x. So we could say that the integral is equal to the antiderivative plus some constant c. The c is the constant of integration, and we need it there because if this was the original equation, and I took the derivative to go back down to my original integrand, there would be no remnants of that c in its derivative. Later on in the week, we're going to figure out how to find that c and find what the numerical value of it is. But for right now, we just need to recognize that there is some constant that could have been there, and we need to represent it by putting plus c. So integration is essentially the inverse of differentiation. So if I was trying to find the integral of 4x cubed, I think to myself, I took the derivative of what and got 4x cubed? Well, that would have had to have been x to the fourth. And again, we have our plus c because I could have taken the derivative of x to the fourth plus any constant and ended up with 4x cubed because the constant would not have shown up in its derivative. So if the integral of little f of x is equal to big F of x plus c, then the derivative of big F of x is equal to little f of x. This means that we can check our work by taking the derivative of our indefinite integral. So if we wanted to find the integral of 3x, I would say I took the derivative of something and got 3x. Well, that would be 3 halves x squared plus c. I can check that work by deriving it. The derivative of 3x squared plus some constant c, I get right back where I started, would be 3x, and that is the integrand that I started with. So obviously there's a pattern. Essentially we're talking about the unpower rule. If I was taking the integral of some constant k times x to the n power, if I wanted to unpower rule it, it would be x to the n plus 1. I add 1 to the power, and I take the old coefficient and divide it by the new power n plus 1. So just like when finding the derivative, if I have a polynomial separated by just addition and subtraction, no multiplication, no division in there, all I would have to do is just find each monomial separately and think about it sort of like 4 integrals. So I would do the unpower rule or find the antiderivative of each one separately and then just tack on a c at the end. So the antiderivative of 5x to the fourth would be x to the fifth, minus the antiderivative of 7x squared would be 7/3 x cubed, plus the antiderivative of 3x would be 3/2 x squared. The antiderivative of 9 would be 9x plus c. Just like with the derivative, we want to put our integrands in calculus-friendly form. So this is obviously an algebra-friendly form. We could rewrite it in calculus-friendly form as the integral of x to the 7/3 power dx, and that makes it a lot easier to integrate. So I do the unpower rule, or I add 1 to the exponent, and it becomes 10/3. And I take the old coefficient 1 and divide it by the new exponent, 10/3 plus c. Now obviously we're not going to write it that way. We're probably going to have, if I keep it, switch it, flip it, 3/10 x to the 10/3 plus c. As we said before, I can check my work by deriving. If we derive this, I get y prime is equal to x to the 7/3, and I end up with my original integrand. In class, and then for homework, I want you to complete the problems shown here. Some of them might be a little challenging. The more challenging ones I'm going to address in tomorrow's video. You can work in pairs and ask questions of your classmates if you get stuck.